Yeah. So this is Coroutines, Async Await, Async IO, and the Pulsar library. This talk is going to be just about Async IO in general and just general musings about it. I'm David Felix. I'm an engineer at Kroger Technology, specifically the Kroger digital aspect, digital customer. So we do like the app that's on your phone, the website, all that stuff. And I'm a services developer on the back end. You can follow me on Twitter at David J Felix. Tweet at me 111. That's also my GitHub username. So go check that stuff out. You can follow along on GitHub, like I was saying. There are some pseudocode or tiny code snippets if you want to check those out. And you can see the slides out there also if you wanted to follow along, or I lose slides or anything like that. For this presentation, I'm using Docker for instead of virtual env or anything like that for my Python environments. If you have any questions about that afterwards, let me know and I'll be happy to evangelize. So what is Async IO? It's a Python 3.4 provisional library, and that provisional is red because that's a little bit of a caveat. It's being put into the standard library, but it is still in a state where it could change without a whole lot of notice. They think it's pretty solid, and it's been going pretty well. But if it does change, they're not going to major version for it. So they're just putting out a warning there. It handles asynchronous I/O and utilities around asynchronous I/O of all kinds. And there's actually a lot to the library. I'll probably be going over a fairly small subset of it and just how I've been using it recently. And it is a language unified event loop. It contains an event loop that it uses to wire all these asynchronous structures up to. And it's kind of the first real language unified event loop for Python. So. You've probably heard some of that technology before already. So why is that new? Where have you heard it before? You've heard it in gevent, gunicorn, uwisg, twisted, tornado, pyuv, pyqt. So like GUI libraries, you're going to hear it in like a lot of web framework will claim event-driven or asynchronous. So it's nothing new to programming or Python in general, but it's new to the language. And I'll be talking about why that's important. I know a lot of people out there are using probably if you're on the web, you're probably using a asynchronous WSGI container, like gunicorn or uwisg. I'm going to try to help differentiate that from actually using Async IO. If that's not where you've heard it, it's not just Python either. Node.js has been really big on asynchronous programming. That's sort of the whole ideology. They use libuv on the back end, which is their event loop. Go has introduced Go routines as a form of coroutine within the language. Nginx, notably, has gotten a lot of reputation for high performance because it uses an event-driven model versus Apache's threading model, or how they used to be a threading model. Game engines will use asynchronous event loops and constructs like this. Java NIO, Erlang EPMD if you're really like into that. But it's not new at all is what I'm trying to point out. And maybe you've heard of Unix or Unix-like environments. They're kind of around somewhere, but epoll, KQ, poll, and select are all sort of in this construct of asynchronously calling something to see if there's something to do. So why do people want to be asynchronous? What point is there to do it this way? Well, one of the big ones is concurrency. With input and output, you actually end up with a lot of these calls that last a lot longer than the CPU needs to do anything. So trying to decouple that CPU from I/O and making sure that your I/O bound tasks aren't slowing each other down. It's really an effort to decouple performant calls from very long calls and make sure that the ones that we can check up on, we're checking up on regularly. In Python, it can also mean fewer processes running your I/O. And in other languages, ones that have POSIX compliant threads, it can mean fewer threads. So you actually end up with a lot less memory overhead and stuff like that. It's also a move to a more conscious control of context switches. If you leave it to processes or threads, you're kind of letting the operating system decide how to schedule it. With asynchronous, you know the very minimum of what you need to check up on the call, and you keep calling back to it and say, is it ready yet? No, then don't bother doing anything else. Just keep coming back to that when it matters. And you can very clearly handle these context switches in a way that really speeds up your code, and it shows. So let's get into some form of an example here. It's extremely contrived example. We're just going to sleep for 10 seconds. And we want to do it 10,000 times. Concurrency is fine. They don't need to sleep. It's all in parallel. And one thing about this is it's not really I/O. You're kind of calling into the system clock to check in every once in a while. But it certainly isn't CPU bound. So this is a good example. And we're going to try to demonstrate concurrency through asynchronous processes. So we'll look at some of the previous ways of doing it, which is like threading. Oh, there's no filter thing anymore. Cool. I was worried that was going to cover some of your code. So here's how you might do it with threading in Python. Notably, Python threads are not system threads, so it's just letting the Python interpreter come back to this element. For something like sleeping, that's actually really great because they're all the same length. When it comes back to them, it's going to experience a surge all at once, and it can handle them all because all of them have something to do when there is something to do. This actually is rather quick, but when you start moving from this sleep function to something more meaningful or something less reliable, like an internet connection. An internet connection to one person might be different from another. So if you have a large JSON response going to one person over HTTP and a small JSON response going to someone else on a much faster connection, that might not be as reliable as 10 seconds. And that sort of difficulty starts to show. It starts to show when you have about 10,000. So one of the naive ways of switching from threading to handle all of your CPUs is, I say naive multiprocessing. This will not run. This crashes my Docker container because I'm spawning 10,000 processes. Surprisingly, some operating systems will handle this really gracefully, but not all of them, and they usually don't do it very quickly at all. The multiprocessing module actually has this parity with threading, so you can do something like this, but it isn't a good idea. So you might do something like pooling, which you would have several pools of processes, like 1,000 processes. That's still manageable for an OS. 10,000, not quite, but 1,000. And you'd have 10 jobs per each one. But the problem with this is that this isn't doing it asynchronously. What ends up happening is the pool item will actually do 10 sleeps in sequence. So sure, you have 1,000 of them, but they're not doing them in parallel at all per those pool members. And then you get like multiprocessing threading, where you're putting them on threads on the processes, and you can see how much this is just expanded with something as simple as sleep. It's really becoming something that I don't want to do. I'd rather just go one thread, one process, and now I don't have to worry about assigning threads and thread pools and processes. But let's throw in some competitors out there. So this is Go. This is not Python. I know, I'm bad. And the reason I have it up here is because there are languages that are doing coroutines right in a lot of ways. And this is something that I look at and I say, how can Python do this for me? How can, going forward, can Python do this for me? And you can see here that we're just assigning this function to a coroutine, and then it goes and does it. This runs in just shy of 11 seconds. The actual processing of 10,000 threads is much shyer than 11 seconds, just above 10 seconds. The actual process of sending those out there is very quick. So I want something like that, but without all like the C-isms that Go has brought in. I want that in Python so that I can do it myself. So here's Async IO, and this is the 3.4 notation. We'll get to that in a second. 3.4 is the newest stable Python right now. There is 3.5 in beta 4. I have a container for that if you really want to try it out. So what you get with 3.4 is you get this Async IO coroutine. So this is kind of nifty because it's creating a generator around this snooze function, and it's saying that we're going to yield a future from this Async IO sleep. You'll note that I did move from sleep from the time module to Async IO sleep. So a lot of what Async IO does is it provides these general utilities, and IO, like I said before, is kind of a not really IO task. You're hitting the system timer, and that counts enough as IO. So this actual task of sleeping is in the Async IO module, and what it returns is a future. So a future is this construct that says, yeah, at some point in the future, I'll have results for you, but right now, here's an object that you can call back with. And when I fan out like this, you notice that I have a little bit of extra around it for starting the event loop, for assigning coroutines to the event loop. So I'm going to use this Async IO wait to wait for all my futures that are in this task. And then when it's done, I'll close the loop and go back to normal non-looping flow. And this is extremely quick. It's quick like the threading example, but it works with something that's not sleep, which is really great. So if I subbed out sleep for something like an HTTP connection where it's not really sure how fast your client's going to be or how fast, how big the object you're going to send is going to be, with that you can actually call back and get them in a manner that will take precedence over the ones that are ready. So if your call is sitting there waiting to stream a little bit more data down your internet connection, we can call back to the function that can actually handle it. Now, I said async await, and async await is a structure that's being introduced in 3.5. This isn't out yet. It's in beta, but you'll note that this is very, very similar to the 3.4. The only difference is that instead of doing the little call to async IO coroutine and doing a yield from, we're using async at the front of the snooze. Yes, it is. And this is actually doing the exact same thing over here. But the 3.5 call is actually working with a coroutine type now, rather than this async IO coroutine. So it's built into the types section. And this notation stems from a C# notation. It's one of the things that they did right in the language. And with the so with this notation, you can get a very clear understanding that this isn't just a generator. This is something that we expect to be done sometime in the future, and that's the whole idea behind the async await notation. This works for any of the coroutines or futures, and I do have a Docker container that you can try it in. Cool. So why not literally anything else? Well, with gevent and a couple others out there that were pretty prominent during Python 2, you actually have a lot of monkey patching where you're changing the way that Python works in order to do this. You don't have to do that. With Async IO, they're providing a lot of the basic level plumbing so that you can do this all very easily. It's also Python 3 compatible, which is really great. There are some back-ported versions of it. I don't know much about them because I'm like gung-ho Python 3, right? Like you should be. But it is Python 3 compatible. Moving forward, it'll be Python 3 compatible. It's in Python 3. And it has this unified event loop that I've been talking about, the one that you can see right here. the Async IO get event loop. So what's nice about that is that when you start mixing in other libraries, there is a standard to go to. You can't say like, oh, I prefer gevent over twisted, and now I'm mangling the two event loops, so I have one loop that needs to be extremely tight, and then another loop that needs to be extremely tight, and then some way for them to coexist without wanting to kill each other. With Asyncio, that's not the case. I'll show some of that with Tornado. But you have this loop that everybody plugs into so that there isn't this fight over whose event loop is the right way. It's a language standard.
So is that example that you just showed, is that all running within a single thread?
So in Python, yeah, it'd be the main thread. It's also the main process, yes. So it's all running in just the single Python interpreter that you started. It's all running in one Python thread, which is just the Python threads don't map to actual POSIX threads. So it's all running right there. Okay. So also with web programming, which I think is a popular use for Python, but that's me echo chambering in my own brain. With web, async is clearly showing benefits over anything else. Nginx took a huge market share from Apache when they were doing event-driven HTTP server, and Apache was spawning threads. It was a huge way to overcome the 10,000 connection problem, the C10K problem. And the big point here is that with Async IO, that doesn't stop at your WSGI server. So the typical way of working right now, if you're not using an event-driven framework, is that you'll have gunicorn or uWSGI running your WSGI container. And that's actually interacting with your web server on a level that is asynchronous. And then when it gets to you, it synchronizes those objects and calls functions that are long calling, that are blocking. But since those are all done on your local machine, it tends to work out pretty well for most cases. There are some edge cases where you start calling out, and perhaps you have like a job queue to handle those edge cases. Now you don't really have to. It extends past your WSGI container into your application because of Async IO. So 3.0 is very fresh. I think of it as like 2014, and I'm like, oh yeah, I've been using that for a while. But for a lot of people, that's still extremely fresh. It is in Ubuntu, but you know, that can cause some concern. But look who's already using it. So Tornado has an Async IO. It's capitalized funny because that's the way Tornado did it. You can tie Tornado into Async IO already. AIO libs is a GitHub repo that's out there, or GitHub organization out there, and they have repos for Postgre that maps exactly to PsychoPG. They have ones for Redis, ZMQ, MySQL. There are a lot of modules out there that already do a lot of the Async IO plumbing for you, and are doing it in this single loop. It's very much like the way that people started porting things to Twisted, except now you don't take on this Twisted dependency. You take on the standard library, which is much less disconcerting, I think. Also, you'll notice Twisted is at the bottom there. Twisted has a migration path listed for Python 3. And one of the big things that they want to have is they want to have Async IO compliance. So before, Twisted was its own event loop, and it was all written in C, and it was the Twisted way of doing things. It was very good at what it did, but they had some tough problems getting up from Python 2 to Python 3 because a lot of it was in C. With the migration path to 3, they've listed Async IO as one of their top priorities, and I think that's really great. We'll start seeing some of the Twisted libraries back again, and hopefully tied into some of these utilities, because they are really great at providing performance in Python. So I know there's a Postgre talk. I actually changed this because I saw that. There's a Postgre Async IO. It is at 2:30, okay. I'll be there, you know, just pitching other talks at my own. So Redis Pi, I really like this library, and it is blocking. Redis is a huge consumer of an event-driven mentality. The way that they keep Redis so fast is using an internal event loop. So it doesn't make any sense that we should have something downstream that's not consuming it in a similarly quick fashion. So AIO Redis attempts to map all of the calls from Redis Pi directly into an Async IO wrapper, so that when you call it, you're not blocking on a delete function here. So when you call redis.delete, you're actually going to get a future back here, and we can wait for that to complete, or we can just get a future and say, that's fine. This will typically be called from some other function, and it'll get called back when it's ready. So with this transaction, we're staging the transaction. We're putting these actual increments into the transaction, but we're not calling out on the network. Those aren't expensive calls. We don't have some variable length call that's going to happen, so those are fine to do right here. But when we have the execute, that's where we have it. So really, these little changes happen, and this is using the 3.5 syntax. But the AIO Redis guys, all of their examples are using the yield from. So wherever you see await, yield from. Wherever you see async, you put an annotation, async IO coroutine. That's the way that you make it 3.4 compliant. It also will migrate forward. So that's one of the neat things that's out there. This is a really great way to work with Redis, and it works with a lot of event-driven frameworks like the one I'm going to talk about. So a less contrived example. WebSockets and a WSGI container. WebSockets, if you're not familiar, are like this continuous connection between server and browser, and the idea is that the server can stream things to the browser, and the browser can stream things to the server. It's really like an open connection with a little bit of annotations on how they communicate back and forth. It's getting a lot of attention because some of the containers, like WSGI, have a hard time handling something like that. They don't really handle like having this open, and people have kind of given up hope and gone to Node.js or whatever you want to say, and use Socket IO as a way to handle their WebSocket, but they still code their WSGI portions in Python, and that's kind of a weird mentality for me, having half of your app doing the real-time stuff over in another language and half of your app over in Python. So we're going to try to do it all in one app here. We're going to do REST for the pub, because that really doesn't need to be WebSockets. A lot of people just want to do WebSockets and everything, but we can use a post on a URL, and we'll just post, and then it'll go out to the WebSocket. So I'm using Tornado for this part. Tornado was asynchronous before Async IO was in Python. It is very established, I think, and it can now use Async IO. But I'm going to show you Tornado to demonstrate that a lot of what Async IO provides, you don't have to worry about. Tornado is nice about abstracting that away. I forget why there's a blank slide there, but so what we have is we have two handlers. We have a WebSocket handler that subscribes, a publish handler that you can actually post to, and we've got our hacky database here. So I wanted to use Redis for this, but I didn't really want to bog it down with a whole lot of database details. So we're just going to put everything in a global dictionary, which is the best. That's the best database that money can buy. It's so stable. So the nice thing that you'll notice here is that really I didn't even import Async IO. I'm just telling Tornado that I want to use the Async IO platform. And all of the stuff that already existed with Tornado, all of the code base with Tornado, is very easily mapped to this new integrated event loop. So anything that I write, like AIO Redis, AIO Postgre, if that's running in the background or if it's running in some other portion of the application, I'm not spawning a new event loop. I'm not creating loops within loops and making what should be a tight event loop a much bigger event loop. It's all in that one Python-controlled event loop, and it's all controlled with very explicit calls, and that's sort of the point of having it. So this is really great because all you have to do is say, I want to, when it's open, I want to add myself to the list of subscribers. When I close my connection to the WebSocket, I want to remove myself from the subscribers, but there's nothing in there about posting. That's all in the normal WSGI handler. So if you've used Tornado for non-WebSocket stuff before, this part, the publish handler, is completely the way you do it except for the write message portion. So that's just saying, for everybody that's attached to a socket, send them a message. And that is an Async IO call. And you don't see a yield from, you don't see an await. That's all behind the scenes. All you see down here is your event loop that's using Async IO. It's so elegant that it stays out of the way, but when you need it, it's there so you can build things. And I think that's really what oh, one more thing. There's a bug in here. We'll come back to it in a sec. So if you have the code up, figure it out. So Async IO is really the plumbing behind the scenes. You don't always see the plumbing, but I assure you, it's great. The common features that you have in the language, a lot of the things that you'll call frequently, like a TCP connection, a UDP connection, an HTTP client, those are all written as coroutines, as features in async await. Sleep is already one. Just all the little things that you could possibly have a callback on are already plumbing. And if you decide that you need something on top of that, they have the utilities to do that. So most of that doesn't surface in normal code. And that's really great for when you're trying to get that into production or you're getting it to people that need to consume it, because teaching somebody about futures, really, you're bogging them down with a lot of time when they just want like a blocking call that does it very reliably. And when you look at something like this, there isn't a whole lot of like, oh yeah, you should be using a future here. There's none of that caveat. Just write the message, and it writes it in parallel. So you have these tools available for custom plumbing if you need them, and a lot of people are already out there building them. I've been doing a ton of Tornado stuff. I like Tornado, but I've been keeping feelers out there, and I noticed one called Pulsar, and it's in the name of the talk. Tornado isn't, because I think it's really interesting. I think it's moving forward. It's going to be a really cool library. It is built on Python 3.4 very explicitly, so it's very like I'm up here on the bleeding edge. So just as a warning. It has a lot of web utilities like Tornado, so you can get a lot of the WSGI container, you can get the WebSockets, you can get an asynchronous HTTP client, a lot of the stuff that you expect from a suite like Tornado, but it's built into an actor-based Async IO framework. So what they've done is they've taken Async IO, this very nice plumbing feature of Python 3.4 and up, and they've created an actor-based framework. The actor model is sort of popular amongst like Erlang, and I know this is a Python conference, not an Erlang conference, so why is that actually cool? So actors are cool for the reason of the bug in this little web server here. So spoilers here, cover your ears if you're still looking for it. If I try to run this in parallel, like on multiple Python instances, it doesn't work. The reason for that is this is keeping a local database of the sockets, but even if it wasn't, they'd still only be connected to one. So when you open your WebSocket, if I have this behind a reverse proxy and I say every server should be the same, they're not. So you run into this problem where if I publish to this one, I'm only publishing to the server here. That kind of makes things annoyingly stateful for a framework like this. So what we want to try to do is we want to pull that away. And that's where actors can come into the work. A lot of what actors do is currently being done by like job queues or workers or something like Celery or message queue. But the neat thing about actors is we can do multiprocessing through actors. Python is going to be on one processor, which is probably why you want to run it through a couple. So that example back there, I would be running it on multiples. So multiprocessing is really great for for spreading this out and getting the most out of your machine. Each actor can be working on its own loop in its own state and not affecting each other. With Pulsar, you can address each actor by name. So if you want an actor that only does WebSockets, or you want an actor that only does WSGI, or an actor that only sends emails, you can do that if you really wanted to. And you can send them work from the arbiter, which is the leader. A lot of this is all very familiar in a language like Erlang, where actors are very prevalent. And I think seeing this in a framework for Python and seeing it be something as easy as Tornado is really great. That being said, I don't use it in any production apps. So that's my caveat. The difference is from other frameworks is that you kind of have this message queue within your app code. A lot of times what people will do is they'll pull the message queue out and they'll say, send that to the queue, we'll get to it later, especially with stuff like emails, where the call could be extremely long. Rather than doing that on a separate queue, rather than sending it out to Celery or Redis or anything like that, it's much closer to your app code, because now that's just an actor. You're explicitly offloading this work, and I'm trying to drive home the explicit. One of the big things that drives me to Python is the explicitness of calls. So explicitly offloading the work and explicitly making these context switches is much better than having things just be funny sometimes, you know? So being able to manage these workers in a way that is reliable is a pretty big trade-off, and you get this trade-off of control. One of the problems is that now you have all of it in app code, so you can't really offload the work. So, like I said, there are alternatives to an actor-based flow. You could be using Celery, RabbitMQ, Redis, Disk, but those wouldn't be within your app. Those would be outside your app. They would be external. In a lot of cases, those are okay to do. But I think going forward, this actor-driven model is going to be something that's really a clever way of working. So where I would have something like this publish handler, this would all be in a web actor. And when I go to actually handle the WebSocket, what I'm going to have to do is I'm going to have to say, give me all the subscribers. Don't just give me the subscribers on the box. This hacky database doesn't work anymore. Give me all the subscribers. I could say to all the actors, anybody who has a hacky database, give me the hacky database. That's fine. You can handle that flow and call out to your workers and say, come back to me, and we're going to go publish it back out. And all that can be done asynchronously through Async IO. It's an interesting paradigm that's being added to Python, and I think it's a good place to watch for the future. Are there any questions? I'm pretty short in time, but yeah, there's been a recent push, at least in C++, for stack coroutines. So do you know of anything in Python that would be able to have a very lightweight coroutine? I know there's stackless Python, so I don't know. So I think probably the smallest thing that you're going to find is going to be like the coroutines as actors. So coroutines themselves have a pretty light stack. So sorry, repeating the question. Is there anything that's like a lightweight coroutine? You would just use the coroutine. You're going to end up with some shared memory, and that's kind of the reason that I like actors, is that when you contain them within an actor, you're saying you can be run wherever you want. You can be run on another processor. You can be run in another VM. You could be run on a network segmented hardware. So you could actually have a very distributed application, and the coroutine would run within that. The problem with that is that now you have this whole interacting in a distributed fashion. Is you have to send the message, you have to receive the message, all that adds network layers. So. Anyone? It's a little bit, so the question is, I'm not using Pulsar in production. Why is that? Is it because it's so new? Yes. So right now I'm working with the Pulsar GitHub repository to try to beef up their documentation. The documentation's a little bit sparse. It says, here's all these great things, and then it doesn't say how to use them. And with Tornado, it's really great because you can say, this is how you use them. Moving to an actor-based flow is really, it's a different way of thinking about things. So having good documentation on that is really necessary, and that's the primary reason I'm not using it. Like I said, I'm not afraid of Python 3.4. I've been using it for a while. So the fact that it relies on Python 3.4 is just, it relies on Async IO. That's the reason it exists. That's the primary reason I'm not using it in production, is because I'm still learning it for the most part. But if it follows the principles of Async IO, I think I'm pretty keen about it, and I'd like to try it, especially if it can give me Erlang-like actors, which would be great for distributed programming.
Docker instead of a virtual env.
Yes.
Can you talk about that?
Yes. So, all right. So this is a Docker file, and I'm actually getting the Python 3.5 beta 4 binary from Python and injecting it into a Debian-based container. The reason that I'm doing that is because rather than handling these virtual environments, I can virtualize everything. So I can have the file system virtualized. I can have everything within this container in a way that isn't going to affect other ones. So when I'm running a 3.4 container, which I do frequently, my 3.5 work isn't overlapping that. So if I have a library that's slightly ahead so that it can make use of async await, or it is in its code, and I want to test that out, I can have that in there rather than having, so it's the same principle as virtual env, but instead of that, you get a whole lot of extra features. One of the biggest ones for me is that when I go to give it to my ops guys to run it on a machine, the only thing I have to teach them is Docker. I don't have to teach them something new about Python or something new about Java or Ruby or anything that they're running. And you know, if you have a couple languages out there, your ops guys are getting tired of learning NPM or whatever new flavor of package manager there is. Docker is really great about just giving you, so it'll give you pip in here, in this one, and then when I'm running my actual, I'm looking at the wrong screen here, I should just look at my screen. So when you actually look at the samples here, for the Async IO one, my Docker file is like that simple. So it just runs Python, and then I'm running a C profile to sort of get an idea of how long those are actually taking. But that's it. It just does that. Does that make sense? Somewhat? Yeah, somewhat. We can talk more about it later. I'll happily evangelize.
Do you know if they are going to depreciate the coroutine generators?
So are they going to deprecate the coroutine generators? So I think there is an intention to do that, sorry. But I'm not positive what it is off the top of my head. I know exactly where to find it, and wow, there we go. You know, now Google, oh, you visited this page many times, all right. You can see, if you go to Python 3.5, they'll say exactly that. So tasks and coroutines. So if you go back to the 3.4, it'll actually say that it's tiny font, okay. If you go back to the 3.4 one, it'll actually say the coroutine generator there. In 3.5, they've actually migrated that from async IO.coroutine, which is a generator like abstract, to a built-in type. So it's written into C. It's written into the C portions of Python. So you actually call the coroutine now through types.coroutine rather than through async IO.coroutine. So I think there should be plans. Like I said, the way that they're going to do it is probably like over several versions, especially since they already released it provisionally. But there was no promise that that was going to be stable. That was sort of the provisional portion. Does that help? Cool. Bueller? Everybody makes a joke.
at the risk of actually calling them lambdas, can you use the async word or keyword on a lambda? Or is that yet another thing that Python lambdas don't do?
That's that's actually a good question. I have not tried it. I'm going to look into that now, actually. It's probably not, I hate to say it, but it's probably another thing that Python lambdas can't do. Do you know off the top of your head that whether or not lambdas can be generators? Okay, so it builds a lot on the generator syntax. So if they can be generators, that might make me lean more towards them being able to support it. I can take a look at it and get back to you though. So. All right. Anybody else? We've got plenty of time for questions. So follow me on Twitter. Tweet ones at me. I don't care. Yeah. I hope the talk was enjoyable. Thank you.